all of them together. If I go back to traditional risk assessment, you're typically looking at problem. If that, most of it is focused on large earthquakes and earthquakes. And what we want to be able to do is a functional analysis of the flow control. So if you do a functional analysis, you know how it works, and you determine how it fails. And really, the things fail because of what we call unusual combinations of usual conditions. We had a case where a rat got into the powerhouse, shorted the exciter of the generator. Generator went offline, powerhouse flows were lost. Switch over to the low-level outlet, which hadn't been maintained properly. It blew out, so we couldn't use that. Then we had a second low-level outlet, which had never been maintained at all, because we never going to use it, and it blew out as well. So we lost complete control of the reservoir. So this problem can only be addressed by looking at the physical and functional arrangements between all the parts. Now, here's another thing if you're working with quantitative risk numbers that you need to be very careful of. Not all risk numbers are equal. Risks that are within the control of the owner are much less acceptable than risks that are outside control of the owner. And if you go back to that messy diagram that I showed with all of the connections, etc., that's where all of the incompetence, the negligence, the cracking corners, all of these things happen. It's at that level that maintenance budgets are cut, or our engineers would much rather be doing big projects, so they don't bother with these little things. The little things matter. And it's all covered in the book on operational safety of dams and reservoirs. The independent forensic team found that the reasons that we justified this book for, all but one of them happened at the forum. So if we really want to make sure that we are managing the vast majority of our risk from dams, it's the operational safety that matters. Thank you.
Thank you, Des, for a very interesting talk. It was actually quite a good follow-on from your presentation yesterday, where you introduced some of these concepts, but you've fleshed out a little bit more the theme of operational mode and the failure mode, which is an interesting sort of concept to take. So thank you, appreciate that. Now, in terms of the program, the revised agenda actually has, I'll be presenting a short paper from the use of risk assessment, or the use of risk in the management of Hydro Tasmania's risk portfolio. So I will just move, and you can keep me on track. So I have 15 minutes.
Yeah, please.
Okay. Hello. Thank you. I'll stay at the lectern so that I don't stray away too far. So I'll be giving you a presentation just talking about the use of risk as a basis for portfolio management, and using Hydro Tasmania as an example. So for those who are not aware, Hydro Tasmania is the state government-owned utility in the island state of Tasmania, part of Australia, and we manage a large hydropower network of dams and infrastructure to provide hydropower for Tasmania. We're also connected to the mainland electricity supply. We produce the largest quantity of renewable energy in Australia, although we're a state with only 500,000 people. So the outline of what I'll be talking about is just the use of the elements of a dam safety program, where risk is used in that program, how that is driven or guided by the principles of ANCOLD, that's the Australian National Committee on Large Dams. And then I thought I'd put in just a little bit on the use of risk-informed decision-making for things other than major safety upgrades, things like a surveillance program. And then I'll give you an example, talk a little bit about our portfolio risk assessment that we've done across this portfolio of 200 dams, and then the types of works that's driving as well, with one example, talking about the Royallen Dam upgrade. So a very generic sort of process for dam safety, very important to establish the context for the business, the internal context and the external, the regulatory, insurance and the public expectations, which are certainly increasing in the Australian context in recent years. Then you have a range of activities that you undertake around surveillance, operations and maintenance, a lot of personnel, emergency preparedness, information management, some very standard activities that you would find in most people's dam safety program. And then we've included in there more of an overt process around performing risk assessments, which I'll talk a bit about further. Flowing out of that is a range of activities to rectify any deficiencies that are found. So of course you need a feedback loop for that process, whereby every time you identify a deficiency, you ask the question, is it tolerable? If it is, then you can proceed, potentially just monitor, continue to watch the risk, see if that changes. If it doesn't pass your tolerability criteria, then obviously there's some rectification to be done. So that's just a very basic conceptual framework for managing the program. In my paper I presented the elements that ANCOLD list as being pertinent to a dam safety program. Now I'm not going to talk through all of those, just to highlight that a number of those quite overtly talk about risk and the application of risk in terms of implementing the program. I couldn't help putting in a few photos of some of our better dams. If you're going to a dams conference, you have to look at very nice dam structures. So Gordon Dam's very famous within Australia. It's not as high as some other international double curvature arch dams, but it's a very iconic dam in Tasmania. So the main ANCOLD guidelines that help drive what we do to manage our program. There's one on the guidelines on dam safety management, and I'll talk a bit more about that in a minute. The second one is the guidelines on risk assessment. And then outside of that, there's a range of other guidelines that have been presented. Now, I was very pleased to see that the conference opened yesterday at the inauguration with the launch of a range of documents produced by the DRIP program by the CWC, which will be available to all the participants. I'm very keen to have a look at those and to see what the content of some of those guidelines are. But these are the ones we use to drive practice in Australia. So in terms of the guidelines on dam safety management, it covers fairly general areas, including the accountability of a dam owner, the purpose and the elements of a dam safety program, the role and the carriage of a surveillance and monitoring program, the importance of operations and maintenance, emergency preparedness, reporting and review. Again, reasonably straightforward elements, but it's very helpful to have some guidance, particularly when those guidelines receive peer and international reviews, so they have some level of credibility, and they're often adopted by a regulator. The regulator in the regulations that are state-based in Australia may well reference the ANCOLD guidelines. So in terms of managing dams, I noticed one of the speakers yesterday actually said that dam safety really is just a part of the asset management process, and I definitely agree with that. So a very generic asset life cycle where we plan, develop, operate, maintain, refurbish and then decommission our assets. And alongside of that, there's very typical sort of asset failure curves that people would be familiar with. Now, this is not specific to dam assets, of course, but just conceptually that idea that assets will generally have some kind of failure probability associated with their original implementation and operation. Then they go into an operational phase where it's conceptually a more sort of static failure rate. And then at some point in time, as they deteriorate, they'll have an increasing level of potential failure. Now that's often referred to as a bathtub curve. Another typical type of asset management terminology to think about is conditional performance of an asset over time. And so this probably applies a little bit more to some of the civil assets that we're referring to, so dams, intake and outlet structures, civil assets like canals, waterways, conveyance structures, those sorts of things. Now again, conceptually this just says that over time the condition of an asset is going to deteriorate. That's just a function of the asset life cycle. And so there's a number of ways we intervene to try and maintain the life cycle of an asset. So you have time-based preventative maintenance activities, condition-based activities, or you have reactive activities whereby you identify a deterioration or a fault or a failure and you'll go in and rectify that. Now, each of those three processes have some validity, but trying to, when you've got a whole program or a whole portfolio of assets you're managing, trying to get a rational basis for deciding what level of intervention to undertake on your assets is actually quite a complex process. So for Hydro Tasmania, so what we've sort of more overtly chosen to do is bring some kind of risk perspective into the decision-making process into that asset management cycle. So that does include the portfolio risk assessment, but it also includes other things such as using a risk basis for decisions around your operation and maintenance or your surveillance practices. So why we found that important is that Hydro Tasmania has 204 dams in the portfolio, but as I said, we're only an island state of 500,000 people. So in fact, the customer base and the revenue base that we use to manage those assets is not particularly large. So it's very important that we find ways to make sure we optimise the application of resources to the management of the portfolio. So when you look at this, we do have a significant number of what we would consider high and extreme hazard category dams, the more important higher profile dams. But we also have a very large number of quite minor structures in the portfolio. Now, one of the issues we find is that for those structures, if you don't give them very much attention, the actual likelihood of having a failure in that portfolio is actually relatively high compared to the rest of the portfolio. So from a brand, reputation, stakeholder confidence perspective, managing the assets in the low hazard categories is actually still quite important, although on a risk basis you would tend to put your efforts and your time into some of the higher hazard category and potentially higher risk assets as well. So when you're talking about some of the fundamental activities in a surveillance program, visual inspections is probably at the very front line of that. And so here's just the table that comes out of the ANCOG guidelines that gives guidance on the inspection type and frequency. So you can see in here that it says that everything from routine visual inspections on a daily basis 3 times a week or monthly for certain types of dams, through to intermediate, which is generally thought of as an annual inspection, but maybe sometimes 2 yearly or 5 yearly, and a comprehensive inspection on a 5 yearly basis. So that's just the guidance in the guideline. This is the actual image. I reproduced it because the text wasn't very good. This is the image that comes out of the guideline that describes that. And you'll notice below it there's a note that pertains to those inspection frequencies. What that note actually says, and I'll read this out, dam owners may undertake a review to determine if a reduced or increased frequency is acceptable. The review should be carried out by a dams engineer to take into account such matters as regulator requirements, dam hazard and risk, type and size of the dam failure modes and monitoring arrangements. And the reference there is to a paper produced by Andrew Pattle in the late 1990s. Now, Andrew Pattle used to be the dam safety for Hydro Tasmania, and we put this paper forward at an ANCOG conference some years ago, and it was in fact adopted and reflected in the guideline. And what that was saying was that there is a rational basis. If you have a rational basis as an owner to vary the inspection frequency other than what was prescribed in the guideline, then you're entitled to do that, and you can actually mount a defensible case that represents good practice. The same thing applies, I think, for monitoring installations, the frequency and type of monitoring that you would undertake. So again, this is the table that comes out of the guideline that would sort of provide guidance around that. And the thing that I wanted to move on to, this is probably something that would be quite familiar to some of the audience. At one of the ANCOG conferences, I think it was about 2006, Mr. John Smart, a former senior officer of the USBR, presented what he called an instrumentation review decision tree. And what this really is, you probably won't be able to read all of those, but it combines two things. It combines a failure modes type of thinking and an event tree process to give a rational basis for trying to rationalise the instrumentation that you would need at a particular dam. So I think most dam owners would have had the experience where you design and implement an asset. It's at its construction you would install a range of monitoring and instrumentation, and then over time some of that might tend to deteriorate to the extent that some instrumentation would fail. The obvious thing to do is go back and immediately reinstall instrumentation, but actually what occurs a lot of the time is that the actual reason for doing that, say that was 20, 30 years after the dam was first commissioned, the reason for that instrumentation may have passed. It was something to monitor the original first filling or the commissioning phase of the storage. And so without going back and doing a fundamental first principles review of the need and the purpose of that instrumentation, you can't make a good decision as to whether to replace it. So all it does is it lists 8 specific questions to work through in a structured process, and depending what answer you get from the undertaking those questions, it will lead you to a series of different conclusions about what you should do. Now, in Hydro Tasmania, what we've tried to do is overlay over that the results of our portfolio risk assessment, because in doing that, we do a lot of work on understanding the dam, its inherent failure modes, its history, the way it's been performing, and then obviously out of that comes a risk assessment. But the information that you gather on the way is actually very useful to apply for other purposes in the dam safety program. So by bringing the output of a portfolio risk assessment together with the framework proposed by John Smart, we've now implemented a way for having a rational annual review of instrumentation at our dams. So I don't expect you to be able to read this, but it's just trying to show that you can actually bring risk-based thinking into your surveillance program rather than just using it to try and understand what sort of dam safety upgrades you might need to do. So the other part of this then is the actual guidelines on risk assessment, and this is generally where the initiation of a portfolio risk assessment will occur. So it covers the purpose, the conduct and the levels of a portfolio risk assessment. It talks about the importance of gathering data and presenting the level of uncertainty in the assessment all along the way. Then assessing the failure modes, and this guideline is under review at the moment, and I'm sure that some of what Des has spoken about operational modes versus failure modes will need to be considered by the review committee on the guideline. Then you have to consider the limits of tolerability and then the extent and the rate of treatment of any intolerable risks. So at a very conceptual level, when we undertake a quantitative risk assessment, we're just looking at a combination of probability and consequence of a range of events. These can be hundreds or thousands of different events depending on the complexity of the assessment that's done. But at a very conceptual level, you get a whole range of individual paired events. And so what we do is we compare them against a line of equal risk, which if plotted on a log-log scale will be a line similar to that one. And then by aggregating those risks, going through a structured process of aggregating those risks together, we then compare that with the line of equal risk. And I only show you this because where that point is at the moment, the blue circle on that curve shows what we would consider to be the ultimate risk position of that dam. So from a reporting perspective, that's what we report when we talk to our stakeholders about the ultimate risk assessment. So when we plot those on the ANCOL Public Safety Risk to Life criteria, which shows increasingly intolerable risks to the top right and more tolerable risks down in the bottom left, this has been integrated into our business risk management framework as a business so that we can compare dam safety risks to other operational, stakeholder and environmental and market risks. This is the same criteria just compared to some of the USVR guidelines, and you can just see the parallel type of assessment that's reflected in the ANCOL guidelines to what's used in largely in America. And this is the results of so when we did the assessment of our referable dams, so of the 204, 55 of those dams were put through quite a rigorous assessment process. Out of that, we had 12 dams that plotted in a higher extreme risk category. And so those points correlate to the similar point I showed you on that aggregated risk chart a moment ago. So then over a process or a number of years, we developed a program to actually mitigate those risks, and I won't talk about that in a lot of detail today. That's the subject of a number of other papers that are available. But over a period of time, those risks have been mitigated via a range of quick win, structural, non-structural works to the dams and the processes of managing those dams, and then a lot more information gathered to reassess the risk. And this is where they've plotted it. Sorry, this is how they plotted after that initial stage of mitigation. Now that's not to say that they're complete.
Another 2 minutes.
How many?
Another 2 minutes. We have already caused your time.
Okay, I'll speed up a little bit. So this just shows you that once you've done a portfolio risk assessment, there's a whole lot of useful or uses you can put that information to. You can actually look at a whole range of different intervention strategies. So you might choose to undertake works, as I said, quick wins, things that you can implement quite quickly and intuitively. They stack up on their basis as opposed to very large capital works. And you can actually, by comparing the different ranges of options, you can look at the by an amount of investment, you can look at the different types of annualised risk cost reduction that you could achieve, or the life safety risk reduction you can achieve over a period of time. And it's a very useful way of presenting that information to your stakeholders, and particularly for funding requests. So this is my final piece. I'll just show you one example of a dam. This is a 43 metre high earthen rockfill dam in Tasmania. It's quite an interesting structure, and when we did the risk assessment, there were a number of issues that arose with that. So it had all of those items I've listed there were potential risks. So the first of those that we chose to do further investigation on was the stability of the spillway walls. And so you can see even from that photo and the model that was developed, they are quite a slender wall, and there was evidence of deformation of certain panels of the wall, differential deformation at the crest of 40 to 50 millimetres that showed that the walls were moving. So an analysis of those walls showed that with the lack of reinforcement, or the very light reinforcing in them, there was a high likelihood that they were cracked on the rear side. Some investigation was done to try and determine that, and some evidence of cracking was found. So, of course, when the risk assessment was done, that came up as a very high part of the risk assessment. So an initial quick win was done, whereby we restrained those walls from moving further into the spillway by constructing a dead man wall in the embankment and then pinning the wall back to that weight. So that was the initial quick win fix. Then followed some investigation to try and understand the nature of the core in the dam. So a range of investigation procedures were undertaken, and what that led to was the next highest risk was the risk of piping adjacent to the spillway walls in the embankment. So that led us to then excavate down behind both spillway walls, remove the core material and replace that material with compliant filter material to reduce the risk of piping. As you'll see, there's the sheet pile cut-off wall on the left-hand side, so that in an operational storage, if we had a large inflow event, that would keep the water out of the excavation. And we installed a more sophisticated monitoring and alarming process in the catchment to give us warning of inflows and potential for flooding. So I guess that was an example of using both the risk assessment to undertake structured program of capital works, but then to also try and manage the risk during construction. So that dam then has had, out of all the risk issues listed for the dam, we've addressed probably the top 4 or 5 of those, and there's still a number of things to be done, but they've now been scheduled in the program to be done at a later date, because from a portfolio risk perspective, the value of continuing to try and reduce that risk has now been overtaken by other items in the portfolio. So there, I'll leave it at that. So just a couple of conclusions. The use of risk-informed decision-making has been a very useful thing, or a very helpful thing in the discharge of the Dam Safety Program for Hydro Tasmania. And the portfolio risk assessment itself has given us a great basis of information on which to make a lot of those decisions. Thank you.
Thank you, Mr. Swinton. Now I invite the third paper from Mr. Edward E. Flint. May please kindly come and present his paper.
This is on challenging, sir. Yes. Back, forward, and backward.
This is
This
forward.
arrow, yeah.
That's forward.
Yeah, show you.
Right.
This is the laser. Laser one is this one.
Okay. Thank you. Good morning. Good morning. Small group, but a very important group. And I want to thank everybody, and I thank the Dias for inviting me here. And we've heard some good discussions this morning. Now we're down to what Inga's talking about is construction. And what are those challenges do for us when we're out there in the field? We've got some design we have to implement. We got problems. We got things going on. So what I'm talking about here is how do we execute our projects in a time-based manner? And after looking at over, I don't know, 700, almost 700 packages, contract packages for construction and other applications, we found a lot of interesting items. And most of all, we can say that these delays, and I always tell the contractors this, and I tell our engineers during the training processes for construction, is that get that contractor working, because the worst thing that can happen are these delays. Many of my reports say contractor not on site. Why isn't he on site? Here we are, we're building a dam, and he's not working this week. He's on holiday. You know, and the contractors are losing money. They don't understand. So why are we overshooting these schedules, and why are we not doing these things? Because a lot of the times, we don't have all the necessary documents that we need to do the work. It's a learning process. Not everything's perfect. I imagine even with Angus talking about when they're looking at reconstruction of these dams, how do you prioritize the work? How do you get it done and get it done under budget or on budget and on time? And what we find out is that if we do hurry or we don't take care of these small things, the quality of the work is really, I'll say, sucks. It's not good. And but we have other examples where they've gone back in there and corrected it. Our job at CPMU is to oversee this work, and we make recommendations and are finding of non-compliance, and our job is to help them, guide them to make sure this job gets done on budget, and all the work that was recommended to be done is in place. So these challenges, I'll say, there's some basic steps that have not been taken care of. And with, like I said, over 650 contract packages, we have an opportunity to actually address these and use these steps in our implementation of the works. And what I can say is that on my last point here, the results demonstrate the importance of documenting step-by-step approvals. We find some good examples, we find a lot of bad examples of how do you go through the process of every component of each BOQ item has been reviewed, has been looked at, and has been approved, and it's going ahead. Has it been surveyed? Do we know the elevation? Has the shuttering been put in place in good manner? Is it tight? It's not going to sag when you start putting concrete in it. All these little things. Who approved the form? Who approved the concrete mix? Is the rebar at the right spacing? All these things are all on OK cards that we're using, and many of the implementing agencies are now using to monitor the performance of their work. I'm going to run through 10 real quick case studies just to show the problem and the impact and the solution, what we found. Barnett Dam, 30-year problem with seepage and leakage in the gallery, sediment coming in through the gallery. We've identified some of the major problems. The water quality is bad. There's some industries upstream that we cannot drain the reservoir in order to really do what I call a good fix of the dam. So we're using interim risk reduction measures in light of that. One of the things that's gone on here, it's been grouted body grouting 5 times. It's a masonry dam, but it leaks around all the water stops, and nobody's addressed that issue. And we're working on that. They've done some, I'll say interim solutions. We want them to move forward and take care of the water stop problem. But the point is that we have the methodologies now. People say, oh, we can't do that in India. We don't have the people that can do that. Yes, you do. You can send rockets 5,000 kilometers downstream. You can surely fix a defective water stop. The technology is there. So that's what we're working on, and we've got good examples of that being handled right now. Chari Dam. This was a complicated one. Reservoirs filled to crest with boulders, sediment, all highly abrasive, mostly quartzites, I think, on this dam. But what happens? They've tried everything. They put steel plates in the glacis. They put angle iron down around the baffle blocks to keep them from getting beat up by rocks coming over the top. And to no avail. So we're using new technologies here. you're using high-strength crystalline cementatious concrete or other cementatious mortars. And what we have found is that it doesn't always work, even in this case. This stuff is very erosive coming over the top of the dam. So how do we fix those problems? And we're experimenting on another dam up in Uttarakhand using 2 different types of concrete. So we're still learning, and it's a learning process for everybody. And I think we'll be successful on this one. We've totally looked at it. It's being implemented in a good way. Other problems that we've seen are we've got rough spillways. They want to make it better so they get a better flow going over the spillway. They've used epoxy. Our impact on this, it doesn't really seem to work. Or the substrate wasn't prepared correctly. So these things have to be looked at in very good detail with lots of, I'll say, consulting to make sure that this is the best solution for the dam. In this case, the epoxy is already delaminated. So now it's got to be taken off, and that's going to be a hard job in itself. So these things don't necessarily work. So our advice is no epoxies in the general sense on the surface of a glacis. It just has problems. Gudiati Dam, another dam that was when I first came here, one of the first dams I looked at, I said, holy cow, look at that hole in the glacis. Masonry dam, rubble-filled masonry dam, and too much, I'll say, erosion, water coming through the dam when you walked in the gallery is like taking a shower. They're remedying this right now. They also are attacking the water stops in this dam, over-drilling the construction joints, oversized bits, and using hydrophilic sealants in there. So there are ways to fix the problem, and we're handling those. Another dam, Mordhana Dam. This one is, I'll say that I'm a remote sensing guy, geotechnical, but I am a very adamant believer in geophysical investigation, non-destructive testing. If you can't do non-destructive, then you can bore the hole and do a geotechnical investigation of it, receive samples out, take a look at the problem. Here, they decided to do body grouting. And the level at Faro, our examples are, right now, we've stopped a lot of the water, but the water stops were still leaking. The case in point, 216, after body grouting the dam, the seepage level was still the same as it was 10 years ago. So I'm very adamant that when drip 2 or any other drip comes on and any dams come up, do the needful, get that geophysical scan done if you have to, and get some pre-engineering ideas, and then you can go through those and implement those in a good manner. And Port Hundy Dam, the challenge here is vegetation management. And this is almost every dam I can talk about, but this is just a good example. The embankment you see here on the water side has got shrubs that have grown back up again. We had recommended that they pull all these by root. It disturbed all the stone pitching on the upstream. They reset it. And then 1 year later, we're back to the vegetation management problem again. So this says that we have to find better ways to manage the vegetation on these dams. You know, it looks nice, yes, not nice. How do you inspect an embankment dam if it's full of brush, timber? The roots die, the root decays, and it becomes a home for termites. It becomes a water access through seepage to the dam. So there are ways to do this. Environmentally friendly herbicides is one way. I've been using them for 25 years, and it works well. And also, operation and maintenance. I think he's talked about it in your portfolio. How do you manage? How do you get the people out there and budget for these people to come out and do the work in a timely manner on a timely basis? Oh, it's the rains, the grass is grown, and the trees are grown because it's a monsoon period. You know, take care of it. There's not enough staff. I know that, and that's a big problem on budgeting for people to come out and do the work. But there are other ways you can do, like I said, using herbicides to control your vegetation. Another one, this is an interesting one, another one that it almost, the ungated spillway, 125 meters, almost was damaged in 1992. They had a flood event, and the block quartzites downstream just kept peeling off and rolling down the hill all the way up to the apron. And they backfilled it with gabions and concrete. Gabion baskets, rock-filled baskets, and lots of concrete. But they closed off part of the spillway. So with the revised flood, we had to raise the dam. We wanted the full 125 meters. They're putting in now about a 400-meter long, three-fall flume spillway there. So there are solutions. It also had seepage around the right bank canal. They had to go in there and fix that also using grouting methods.
Ed, you have 2 more minutes.
Good, just about finished. Choliar, another dam, 66-meter high dam, that also needs to have geophysical investigation. I think that's being planned. We've done as far down as MDDL, as far as grouting and repointing the upstream face using cementatious mortars. And one other one is, when we talk about work on the downstream side of a dam, any dam, the modus operandi is don't dig holes. In this case, they had a leaky shutoff valve on the downstream side from an old sluice pipe that came through the dam. How do you fix this? It has to be fixed from the upstream side. We've made that recommendation to the agency, and I think they're working on that now. Wellington Dam, upstream slope failure. The downstream on the drip was all done, flatten the slopes. This is a 100-year-old dam. On the upstream, they had fixed 900 meters or 1,600 meters before, but they didn't finish the upstream side to flatten that slope. It sits on very soft foundation material, and she slipped, high water. And now our recommendation is to finish the upstream side all the way to the end. No partial work here. So what I want to say is that the things that we're experiencing here in India during the rehabilitation project, now almost 3,600 crore, are not unique just to India. The problems that we see when we do investigations in the foundation are not unique to India. Calaveras Dam, California, water supply dam, 200 meter high dam, 220 meter high dam, feet dam, and anyway, and it's a water supply system for the city of San Francisco, and it was not seismic stable. So they came in to retrofit for $400 million, 415 for the first contract. Since then, when they started excavating, whoops, we had a slide, an ancient landslide that was unearthed, fell, 1,000 cubic meters of concrete. Relook at it again, more studies. They excavated the right abutment, more failure, another landslide, ancient landslide. Whoops, now we're 2.5 years late. The price is now $810 million. One dam. What does that say? It's that we need to do certain steps to make sure the works get done in a proper manner. And I've listed 6 of them here. And these things, new technology, yes. Construction management training, yes. We've been doing it here. I want more construction management because many of these young engineers don't have the skill set it takes to do this. And also prefabrication of work at Narayanpur. They're prefabricating the bulkhead gates and moving them up to the top of the dam. Very uniform, very tight tolerances on these gates, so they're all working well. And also, the contracts are complicated here. I'd like to see them simplified.
Just a concluding right, please.
Yeah, got it. One more. And communication better. Communicate better. We're having talks with people, and people don't understand, or it's not getting down to the right level. So just to finalize here, skill, knowledge, and ability. This SKA, I call them. How do you do a job? How do you execute that project in a good manner? And also the willingness of the implementing agency and the dam owners to take charge. I want to see more of this. I see good examples and I see bad examples. I want more. And ownership. How do we get ownership? So with that, thank you.
Thank you, Ed. So thank you for the reminder of the importance of, I think in your paper also you made the highlight about the importance of getting good experienced input into understanding scopes and rectification, so thank you. So our next paper will be from Vivek Tripathi, from the Central Water Commission in New Delhi. He'll present a paper on managing geotechnical challenges for safe design and construction of dams with deep foundations. Please welcome Vivek.
So this topic is managing geotechnical challenges for safe design and construction of dam with deeper foundation. So foundation has a threefold function. It's provide stability to dam, provides sufficient stiffness for limiting deformation, and provides seepage control. So this is the general term about the foundation. So planning to access, this is the difficult aspect. Planning to access the dam, deep foundation level through excavation is a major challenge, because for that you have to design, you have to put your coffer dam from greater reaches from your main dam, and diversion tunnel length will also increase. The problem aggravates if the adverse geological features are encountered. Suppose some shear zone or some fault encounters, then the problem will come. So the bedrock exposes the project area, because I am now coming to more specific, from general to specific. This is about the Konasanchu 1 project of Bhutan. So in this project, bedrock exposed in the project area are represented by garnet bearing foliated and jointed quartzite biotite gneisses and quartzo feldspathite gneisses. So medium to high grade crystalline, medium to coarse grained metamorphs rocks with well developed foliations. So this is the geology of the right bank of the total geology of Konasanchu 1 project. So foundation of dam is a determining factor in the selection of type, factors like topography, construction material, availability, spillway requirement, etc. also play equally important role. Generally, where the overburden is large, we go for the embankment dams, rockfill dams. But exceptionally, here we are bound to go for the concrete dam, because valley was very narrow, and the diversion flood was about more than 15,000 cubic. So why concrete dam? So I told you this is the compulsion. Accordingly, it was decided to have a concrete gravity dam with sluice spillway in its body to pass the 15,000 magnitude flood. So these are some typical, this is elevation. Top of dam is 1205 elevation. Height of the dam is 130 meter. And it has 6 bays, sluice spillways. It has 6 bays. So when excavation in the dam pit reached at the level of 1190, then this right side abutment faced a slide of 3 to 5 meters. So the challenge was to put the dam on this slided material, on this slide zone. So for this, about 14 for investigation. 14,000 meter drilling was done. About 37 boreholes were drilled to know the geology, and deeper geological investigation revealed presence of deep-seated two major shear zones along which the slide took place. So slope stabilization was done by grouting to consolidate the slope, micropiling again to stabilize the slope, and cable anchoring. So this is the, you can see number 8 was NSL, and number 1 was proposed cutting profile before slide. And after slide, this slope was proposed to cut according to 2. So this is the plan. It has 6 overflow blocks and 13 total number of blocks. So slope stabilization measure has been done by, from the top, you can see these two shear zones which have encountered this one. This is called, we call it SZ1, and this is SZ2, vertical. So along this slide took place. So we have provided the micropiling, this cable anchoring and grouting. And these two blocks, which is your red piles, these are the 2 meter dia piles. These are 2 meter dia piles on which block number 13, 12 and 11 take place. So this is all plan in where you can see the stabilization measure. So these are the dam blocks, block number 13, these are NOF blocks, 13, 12 and 11. These are 2 meter dia piles on which this dam blocks will come. And for CPS control, we have provided the contiguous piles, secant piling. So you can see this is this red continuous line is the secant piling along this. So this is again the holistic stabilization measure, grouting, cable anchoring, micropiling, 2 meter dia piling. So conclusion, dam can be built successfully even at the site with difficult foundation. Deep foundation and heterogeneous and adverse rock mass at foundation level, as well as in abutment, pose challenge in main dam foundation stabilization measure for slope stability and seepage control measure. So for that, we have provided the secant piling. Thorough geological investigation are necessary to minimize the surprises. So foundation requires some treatment to satisfy the basic requirements I told you, stability, deformation and water tightness. Various measures are available to increase the foundation shearing strength by grouting or by cable anchoring, stability of the abutment, foundation stiffness, and to reduce foundation seepage. Deep foundation and adverse geology at right abutment of Purana Sancho 1 project posed several challenges, just like these 3 challenges: slope stabilization, foundation improvement, and seepage control. We have controlled all these 3 parameters, and which have been tackled using latest technology. Thank you.
Thank you much for a very interesting presentation, and thank you for sticking to the time as well. Some very interesting foundation treatments in that project, obviously. Our next paper will be presented by Kishore Kumar from the Karnataka Water Resources Department. He'll present a paper on the rehabilitation of a 100-year-old Krishna Rajasagar Dam in Karnataka.
Hello. Good morning, everybody. Myself is Kishore Kumar, Water Resource Department. I am working in Water Resource Department, Karnataka. In behalf of Managing Director Kaveri Neeravari Nigam Limited, I am presenting a paper with the kind permission of our SPMU Director. Rehabilitation of 100-year-old Krishnaraja Sagar Dam in Karnataka. First introduction. Krishnaraja Sagar Dam is multi-purpose dam constructed across river Kaveri, and Raja Krishnaraja Odayar IV and Saram Vishweshwarya, known as the foresight and grand vision, had convinced this project, and it has constructed in 1911, started in 1911 and completed in 1932. The construction was carried out only with labor and less machineries, with local materials like Surki mortar. Silent features of the dam is at the foundation width is 33.88 meter, and height of the lowest river bed is 39.87 meter. Width of the dam is 4.12 meter. Length of the dam is 2.62 kilometer. It means 2621 meter. And material for dam construction, it's a local size stone and ruble masonry. There is no drainage gallery in this dam. Catchment area is nearly 10,880 square kilometer, and width of the river at the dam site is 277.44 meter. The capacity of the reservoir is 48 TMC, and historical maximum flood received 6,035 cumecs in 1961. Original cost of the dam is 9.1 crores, and total number of 173 number of vertical gates been in this dam. This is the profile of the KRS dam. Various organizations, CWPRS and DSRP, had inspected regularly, and they have suggested some of the rehabilitation works, so that based on their observation, sweating on downstream face masonry portions between chainage 1460 to 1850 and leaching of pointing mortar at some places, springs of water on downstream 2120 has been found. Damages in seals of gates leading to leakage through these seals, peeling of mortar in masonry joints of apron with pitting of surfaces, distress of on upstream face like deep and wide openings between masonry joints. Downstream side gate piers through masonry leakages are observed. A study suggested for diagnosing causes of distress, rotary drilling 150 mm diameter, which this one borehole videography should be done. These are some of the visual observation initial for the sweating on downstream face, wide openings in masonry joints. CWPRS recommended some of the suitable cementitious mortar for raking and pointing, and grouting of the dam body for improve the density of the dam body. Certain repair material we are used, that one PACC has been used, so that rising 2 centimeter of T joint points. These are the lab tests which are conducted in site, and whatever the laboratory test in this one, KERS has done the work for this one. So based on that, test reports have been there. These are the methodology of upstream pointing. First, initially raking of joints, and after that, the joints will be cleaned with Steripure with water, jet pressure water, applying of bond coat. After that, PACC material with composition of Nicomix 65% and cement is 30% and for 5% of water, so that the the joint of the filling by mortar, whenever the depth is more than 300 mm, 1:3 mortar filling will be done. After that, we will going to put the PACC mortar. Top coat will be the application of top coat after final. Normal procedure for the curing of water, it was done. More than the depth of the 300 mm, we will place on single PVC pipes, so that horizontal nipple grouting should be done in the body wall. Grouting of the dam body. To assess the quality of masonry, borehole videography is conducted and permeability tests been conducted. 2 boreholes of 150 mm diameter at the chainage of 1252 and 1352 has been conducted in the deep of 3 meter foundation rock. The cores recovered were physically inspected by the SPMU consultants and CPMU consultants, and based on that borehole videography report, we have done the investigation holes. This is the report of the borehole videography. 76 rotary holes investigation hole been drilled, and that 50 to 65% of core recovery, and based on that one, 15 to 2983 lugans we are getting in 5 stages. So that in investigation the grouting has been done, and average consumption is 172 kg per meter. In some chainages, some 3 or 4 chainages, the maximum water loss has been got, and also their consumption of cement is also more. Methodology of grouting. From upstream pointing, primary holes it is 1.3 meter, secondary holes is 2.8 meter, and tertiary holes is 2.05 meter, and additional tertiary holes is 1.65 meter of spacing. The spacing of the primary holes will be 12 meters center to center, and secondary is 6 meters center to center, and tertiary is 3 meters center to center, and additional tertiary is 1.5 meters center to center. Total this one 51 to 57 diameter of the rotary drilling is been done, and that maximum depth of the foundation rock is 3 to 4 meters. Alternate stage we have conducted the water loss test to get the efficacy. The grouting executed as per the IS code 1:10, started with 1:10 and ended with 1:1, and the pressure is 3.5 kg, maximum pressure is 3.5 kg per centimeter square. The grouting was considered as a grout of refusal when the intake reaches to 2 liters per minute at maximum pressure of grouting observed over a 10 minutes. For this grouting, we are along with cement, we are adding anti-string grout material for the grouting. This is the waterless test conducted in the alternate stage of grouting. This is the schematic diagram showing that one primary 12 meter center to center, and secondary 6 meter, and tertiary and additional tertiary. You can see this schematic plan. This is the one small animation so that before that one grouting how it is being done, and after grouting this is the body with grouted staking. Drilling and grouting machines in operations. Conclusion. The age-old 100-year dam Krishnaraj Sagar has been successfully rehabilitated by conventional methods of upstream pointing, body grouting after proper investigation studies. The observation and suggested remedial measures by experts during execution were very useful in achieving good results of rehabilitation. The works executed by the agency were qualitative and effective. The quality and properties of repair mortar PACC supplied for pointing of masonry were consistent for each batch of material, were in good agreement with test report of CWPRS. The drip inspection team, especially thanks to SPMU and CPMU consultants, the dam safety review panel members and appointed experts periodically visited the dam to exercise quality checks, and their reports and are satisfactory. The procedures followed in rehabilitation of the 100-year-old KS dam by methodological and executed professionally, duly following safety norms as per suggestion of CWPRS, KERS, DSRP and DRIP team. Recommendation of these institutes were very much useful in achieving the required results. These institutes contribute in correct assessments of damage and remedial measures of dams. Lastly, the sweating and springs of water absorbed in downstream side of the dam after rehabilitation, after upstream phase pointing and body grouting, it has been completely stopped. Drip intervention approach for KRS dam. Being a heritage structure retaining of originality in architectural, aesthetic and monumental ambience with uppermost concern, and all our efforts to enhance the safety and integrity of the heritage structure utilized instead of art and archaeology. KRS dams will serve and inspire the future generation to adopt aesthetic values for the engineering works. In recognition of excellent work done, DRIP and World Bank awarded excellency certificate in rehabilitation of KRS dam. Thank you. If time permits, I can show 2 minutes of video. If you have it now? 2 minutes video. Yeah, you're on it. This is the KRS dam. This is self-explanatory about rehabilitation work. Thank you. Thank you.
Okay, thank you for your presentation and a very interesting video as well. Sounds like it was a very successful project. Our final presentation will be by Alushi Paul from KSEB, talking about repair of cracks using microfoam cement grouting and presenting some case studies for us.
Good morning to all. I representing KSTB. Hello. Good morning to all. I am representing KSTB. I am giving this one repair of cracks using microfine cement grouting. This was done in Idiki Arch Dam. So I will explain something about the Idiki project also. The iconic project of this conference is Idiki, the icon of this conference also. So, Idiki project consists of 3 dams. It is a dam complex consisting of 3 dams, Idiki, Chordoni and Kolamau. The three dams forms one reservoir, and this is a Kolamau dam from Google Maps, Chordoni dam, and Arch Dam is seen right side. That is the right side of the Arch Dam. So, it's a double curvature parabolic concrete arch dam across Periyar, maximum height 555, rest of the dam 25 feet, 75 meter, and maximum base width is 65 feet, so full reservoir levels, and that also the salient features. These are the construction, at the time of construction, the photographs taken during the construction time. And it has got a long-term, time-dependent dam behavior, has got some problem in the dam behavior. It's an upstream progressive deformation of 1.3 millimeter per year after the year 1990. With the instrumentation studies, we got these results. Got it? Hello, okay. Yes, sorry for the troubles, please. The dam has got some time-dependent dam behavior, upstream progressive deformation of 1.3 millimeter per year after the year 1990. It was constructed in 1976, commissioned in 1976. But after the year 1990, the instrumentation data showed some upstream deformation of 1.3 mm per annum. So, and the other behavior is an upheaval of the central crest of the dam, and upheaval is also around 1.5 millimeter per annum. And formation of a generation of a continuous hairline crack on the downstream face of the gallery, upper gallery, in the year 2001 after an earthquake. The hairline crack noticed during thorough inspection after an earthquake, magnitude of 4.6, around 50 kilometers away from the dam site, and it was continuously monitored thereafter. And the crack attained a stability state, and then we, during trip works, we go for a grouting purpose. So this was the crack, longitudinal crack in the upper gallery. Upper gallery means it's at the level of 2,300 level. So the problem with this has got a peculiar dam operation, reservoir operation, because the water will never go 20 feet below. That is upper gallery. So always the water will be standing from bottom to first gallery, always. Because always the water is at the outside. It will never go beyond that. So it's fluctuating from the upper gallery to the maximum 20 feet below the upper gallery, the minimum drawdown level. So upstream is always water, and downstream and other upstream and downstream exposed to the temperature effects. So due to the archidam monoliths are always grouted. So it's a monolithic structure, so temperature fluctuations constantly affect the archidam. So this is the gallery crack that is at the upper gallery. We have tested with the core and the 45 centimeter core, splitted core around. So that was the grand cantilever section. And we have done a film study for this, and during activation of a film study was the low pressure grouting of gallery crack with microfines in the ground. And the next phase is reflective white paint on reduction pathway and slip based down to heat absorption, reduce heat absorption. Then demarking areas of sun explosion. So first thing we shifted up the microfines with grouting done. For the treatment cracks, we removed the loose surface plastic, they cleaned the surface cracks, cleaned the crack surface with the compressed air and water pitch. Cutting through of size 25 cm, 25 mm wide and 25 mm deep along the crack. Filled them. Yes.
You need to face here.
Yes. Cut a groove of size 25 mm wide and 25 mm deep along the cracks and drilled a 50 mm deep depth and fixed 12 mm nozzles along the crack at 2 meter interval and sealed cracks and fitted the nozzles with the Cypex Megamix 2 and allowed 24 hours of hardening. This is the process of treatment of crack we have done. And then grout preparation, we use Alcofine 1108 SR, which is cement manufacturer, and admixture of Cypex C 2010 of 20% by weight, and water cement ratio adopted is 1.1, and we got a Marshcon viscosity of 26. Field testing, we have tested with the field testing Marshcon viscosity, and mixed it with the colloidal mixer for 5 to 10 minutes before injecting, and continue stirring while grouting. And grouting produced adapter water injected through the nozzle for saturate the cracks. The whole the cracks were saturated, and saturated one hour before we saturate the cracks. And grout injection started from the left and the right. And grouting started with a pressure of 1 bar and stopped after 3 bars. And when the grout begins to flow through the adjacent hole, the first hole is blocked, and through the adjacent hole it is injected, and this process continued for sealing all the cracks. And the above process is repeated for completing the grouting. After completing the grouting, the projected part of the nozzle cut and surface finished. And this is why microfine cement we adopted is the grain size distribution is this one. Alcofine 1108 has got a D95 of 15 microns. 15 micron. D95 of Alcofine 1108 is D95 15 microns. And SR is a super plastic radar already. So Alcofine 1108 with SR is a super plastic already added, so that flow is obtained. So, and also the bleeding is very low for the Alcofine. After 60 minutes, the bleeding of the grout is very slow. So we used that. And also properties, we tested in the lab. The Alcofine alone is tested, and Alcofine with a 25% Cypex admix also tested. So for the test results, we got good results, and that's why the Marshcon viscosity only 28. Marshcon viscosity of water is 24. So we got a water apparent viscosity of 28 Marshcon viscosity. So grout is freely get through the cracks and seal the cracks. Slightly bleeding, but we completed within 1 hour. We completed the one mix will be completed within 1 hour. So final setting, this is the result tested with the admixer. And this is the gallery crack actually developed. The maximum aperture of the crack was 1.2. So it was stabilized at that time. After 1.2, then this is the process. Groove cut and sealing is done. The nozzle is fixed, and the finished gallery surface. Gallery. Yeah. So we have done after the studies, and also we have done a geophysical investigation by Parsons Group. Parsons Group, and they reported that the crack depth is 3 to 4 meters to the depth. So, in conclusion, microfine cement coating was very effective for repairing the cracks of the gallery, and this hyperset mix retards the initial setting time. So, because we can use more and reduce viscosity so that it will penetrate deep into the cracks, and it's also generating non-soluble crystalline formation throughout the pores of the capillary tracts and seals the cracks. And so this was our experience. Thank you for all for listening.
Thank you for a very timely presentation. Thank you. Now, we've actually made reasonably good time. We did start a few minutes late, but we do have time for a few questions, if anyone does. Rather than get the speakers to come back on the stage, perhaps if you have a question, we'll bring you a microphone. You can identify who you are and what organisation you're from and who the question's directed to, and then we'll see if we can get the author to provide an answer. So, does anyone have a question they'd like to ask?
So one of my colleagues, Mrs. Jai Adlabadkar, her papers remains to be presented in this session only.
Right.
Yeah, she's there, sir.
Well, we were given a modified program, and it just contained the 6 presentations that we've just had. We didn't have a 7th presentation in this section. Does anyone have a question for the presenters who've presented their papers? We'll take some questions and then we can do it. Yeah. Should we do questions first or do this now? Okay.
Hello.
So we will have
There is one question, sir. Questions.
Okay. Yes, all right. Pose one question, please.
Yeah. Sir, racking and pointing of the RR masonry, is it necessary for any high strength or medium strength or low strength in between the mortar? We wanted to know that. Hello.
Sorry,
Sir, are you under?
The question was to who?
The question is, when we do the repair and rehabilitation work in the mortar, either any other cementitious mortar, are we required any high strength or medium strength or low strength?
Okay. Was your question to a particular author, to a particular paper presenter?
Yeah.
Which presenter?
From KRS.
Hello. Hello.
Yes, sir.
Thanks for your question, sir. Actually, this one initially tested by CWPRS for this one. Based on our Surki mortar and whatever the properties for our dam is necessary, they have given the this one test report of the laboratory test strength. Not only single factor, the 7 factors it is required for our dam. For this one mortar, one is compression and second one is tensile, bond strength and also this one shear, permeability. All these tests were conducted by CWPRS. Based on that, this one we have taken the work and we have done the things.
It is a general question.
Yeah, no. That's why I'm telling that one. I'll give to my expert this one, Shuprasad sir. He will answer your question.
High strength mortar only, as suggested by the CWPRS. PICC high strength mortar has been used, considering other aspects also of bond strength and operational resistance and perviousness, etc. Normally, it's a high strength mortar only.
It is required. Yeah. Thank you.
Thank you.
Okay, thank you. Now, in an earlier version of the program, we did have an additional speaker who has actually travelled a long way to make a presentation. So we'll give her a small time to give a presentation. So this will be Jay Edlabadkar from the Central Water and Power Research Station, Pune. Would like to present a paper on stability and rehabilitation of earth dams, some case histories. So I think it's probably fair that we just make a short time available for her presentation.
Thank you, Chairman and the Co-Chairman, for giving me the opportunity. I'm here to present a technical paper titled Stability and Rehabilitation of Earth Dams CWPRS Case Studies. This paper is basically a compilation of various case studies which we have conducted in CWPRS so far. We all know that earthen dams are massive artificial water barriers which are created by placement and compaction of various complex compositions of soil material, which can be in any form, say soil, sand, clay or rock. And the embankment dams, it is the friction and the interaction that binds the particles together to form a stable mass, unlike any other cementitious material like in concrete or gravity dams. So there are several advantages of earthen dams, like it can be built on any type of foundation. It is suitable for sites where concrete dams cannot be constructed for structural reasons, for example, existence of weak foundation. Since it is constructed out of a naturally available material, that is soil, the cost of construction is low, and it is believed that earthen dams are more resistant to earthquake. But nevertheless, along with these advantages, there are certain limitations also. Since soil material in itself is a complex material, the design, maintenance and construction of embankment dams is more complex. Soil is a permeable material, so embankment dams are more susceptible to seepage. Availability of suitable material in acceptable quality and quantity from nearby borough area is a difficulty, and maximum number of dams which are constructed today are embankment dams, and possibly that is the reason why maximum number of failed dams worldwide are also embankment dams. So it goes without saying that we need to be extra careful about constructing and maintaining earthen dams. So these are a few case studies which we have done at CWPRS for rehabilitation of earthen dams. Due to many reasons, the dam authorities and the dam owners were concerned about the safety of earthen dams. Like that, some of the dams were located in seismically active area, and instead of depending upon the simplified method of pseudostatic approach, the dam authorities felt that the detailed seismic investigation should be done, and hence the studies were referred to CWPRS. During routine site inspections, it was observed that certain adverse situations were existing at the dam site, and hence for rehabilitation purposes, the studies were referred to CWPRS. There were heavy leakages or seepages in some of the dams. Then the stability assessment was also one of the requirements, following an important structure which was located on the downstream of the dam. And sometimes for augmentation of storage capacity also, the dams, the safety of the dams had to be reassessed. So owing to all these reasons, we have conducted stability analysis of many earthen dams. The first case study which I would like to discuss here is that of Dudhwa Earthen Dam in Chhattisgarh state of India. It was constructed to create one of the reservoirs in the Mahanadi irrigation scheme, located around 140 kilometers from the capital city of Raipur. The dam was constructed in the year 1962, but since its first impoundment itself, there were leakages and sand boils which were observed at the dam site. And the result was that underutilization, the dam could not be utilized to its full capacity, and there was also a danger to stability of the dam. So this was the section of the Dudhava Dam, and two critical sections were identified, one at chainage 40 to 42 and other at chainage 82 to 83, which were heavily damaged due to seepage. The interesting fact in this was that the dam was instrumented with the help of piezometers, and there was also data which could be made use of in designing the rehabilitation measures. Some relief wells were also installed on the downstream side. Now our studies began with field investigations. We did site inspection and some soil sampling for determining the physical and engineering properties of soil samples which could be made use of in the stability analysis. We recommended boreholes to be drilled along the downstream. The location of the boreholes is shown in the figure. Soil samples were extracted and laboratory testing was conducted. These are the values of the permeability of the soil material from different zones of the dam, which was made use of in the seepage analysis. Now the seepage analysis was initially conducted for the design dam section, and it was found the blue line which could be seen in the first figure, it was the phreatic line which was obtained from the seepage analysis for the design dam section. However, these pressure head values did not match with the data which was observed from the piezometric levels, and as such it was presumed that the filters and the drains in the dam material were clogged and they were not functioning as per the design. So the permeability of the filter and the drainage material was reduced, and again the seepage analysis was conducted, and now in this case it was found that the phreatic line matched with the piezometric data. So with the elevated phreatic line, slope stability analysis was conducted, and the values of factor of safety were very, very low as compared to the minimum specified value of 1.5 as per the BIS standard. So in this case, there were two approaches for adopting the rehabilitation measures. First approach was to completely arrest the seepage water which was flowing into the dam body by lining the upstream slope, and the second approach was to provide a rubble fill loading on the downstream side of the dam so as to counterbalance the extra seepage forces that were acting on the downstream slope of the dam. So any of these two approaches, based on the feasibility at site and based on the cost considerations, could be adopted. The thickness of the rubble fill loading was also designed so as to achieve a minimum value of factor of safety of 1.5. The second case study which I would like to discuss here is again of a dam which was heavily damaged by seepage. It was comparatively a dam of smaller length of 180 meters, height was around 25 meters. It was constructed in the year 2011, but it was heavily damaged due to seepages and leakages occurring through the dam body and also through the abutment. These are the few photographs of the leakages that were occurring at site when we visited the SAM dam site. Our work started with soil sampling. We recommended boreholes to be drilled into the dam body, and in situ permeability tests were conducted. We conducted the laboratory testing to find out the physical and engineering properties, and we conducted the finite element seepage and slope stability analysis. Now again, for this dam, when the slope stability analysis was conducted for the design section, the factor of safety was found to be very high. That is of 1.94. However, when we conducted the seepage analysis from the permeability values which were derived from the in situ testing, we found that the phreatic level was at an elevated level. If you see at the upper two pictures, you can see that the phreatic level has almost crossed the top berm of the downstream slope. So when we conducted the slope stability analysis with this elevated phreatic line, we found that the factor of safety was coming very low, to the order of around 1. So in this case, since the seepage discharge was quite high, we suggested remedial measures in the form of upstream lining, geomembrane underlain by geotextile, and we also recommended grouting inside the dam body. The third case study which I would like to discuss is that of Ukai Earthen Dam in the state of Gujarat. This dam was constructed in the year 1972 on river Tapi, and it forms the largest reservoir in Gujarat, and it is a multi-purpose project used for irrigation, power generation and flood control. Now if you look at the location of Ukai Dam in Gujarat, the Kakrapara Atomic Power Plant is located at a distance of around 40 kilometers downstream of the Ukai Dam. So the power plant authorities were naturally concerned about the potential risk of the power plant in case of any untoward incident that would occur to the Ukai Dam, especially in the case of earthquakes. So instead of relying on the simple method of zero approach, the dam authorities referred the study to CWPRS for conducting a detailed earthquake dynamic stability analysis. So again, our approach was to start with field investigations, to conduct the laboratory testing. Now in this case, the dynamic stability of the dam was to be conducted along with the static testing. Some dynamic tests were also performed on the soil samples to find out the dynamic properties, and then we did geotechnical analysis to find out the response of the dam. So this is the plan of the Ukai Dam. The location of the boreholes and the trial pits is shown from where the soil samples are extracted. And these are the few outputs from the laboratory testing for static and dynamic condition, and the parameters which are derived from testing were used for conducting a detailed dynamic analysis. The dynamic analysis again consisted of 3 steps. First is the response analysis, where to apply a site-specific earthquake acceleration time history of the dam, and you find out the actual acceleration and the induced shear stresses in the dam body. And based on this, the second step is to find out the strains that would occur at each element at each node in the dam body. And then finally, in step 3, we find out how much the dam body would actually deform. So this method certainly has an advantage over the zero-static method. Zero-static method gives you the safety or stability of the dam in terms of only one value, that is the front of safety value. But here you actually get how the dam body would deform in the event of an earthquake. So the results of this study were like the crest settlement was to the order of 0.02 meters against the freeboard provided 6.1 meters. So it was found that not much damage would occur. There would not be any overtopping to the dam. Maximum horizontal crest displacement was around 0.31 meters, and these are the values of maximum vertical and horizontal displacement that would occur at a particular node in the dam body. So it was concluded that Ukai Earthen Dam can withstand a design earthquake having maximum ground acceleration, although local and insignificant yielding in smaller zones near top of the dam can occur. So to conclude, based on the studies, I would like to say that there are many rehabilitation measures which are available, but selecting and designing the optimum remedial measures is a skilled task, and there is no generic solution which is applicable for undertaking dam rehabilitation measures. Owing to the site-specific characteristics of the projects, a detailed site investigation has to be done for every site, and a detailed analysis based on numerical methods has to be done. Numerical methods, they provide a great tool for design of optimum rehabilitation measures, because we actually get to know what is happening inside the dam body, and instrumentation, apart from providing information about health of the dam, the data can also be made use of for designing of rehabilitation techniques. Thank you.
Okay, thank you for that presentation. Look, thank you for sitting with us. We did get an extra presentation. Sorry, we won't have any more questions. We're getting very close to having the break. I'd like to ask you to thank the various speakers for making their presentation to us, please. And we'll now move to close the session.
Before we conclude this session, on behalf of the organizing committee, we would present a token of appreciation to the speakers. I invite Mr. Angus to give away the windows to the speakers. First, I would love to invite Dr. Desmond Hartford to collect the window. Chairman. Thank you, sir. I would like to invite Mr. Edward E. Flint to collect the memento. Thank you, sir. Next, I would like to invite Mr. Vivek Tripathi to collect the memento. Thank you. Next, I would like to invite Mr. Kishore Kumar to collect the memento. Thank you, sir. Next, we would like to invite Mr. Elaushi Paul to collect the memento. Thank you, sir. Next, I would like to invite Mr. A. S. Edbecker to collect the memento. Thank you, ma'am. The chairman will be presenting a memento to the co-chairman, Mr. A.K. Genju. Please, sir. Thank you, sir. And next to the director, Mr. D.S. Chesker. Next, I would like to invite Mr. Ed Flint, dam safety specialist, to give away the plate and memento to the chairman. Thank you. With this, we wind up this session. Thank you.